So just starting off this video from where we were last time, let's recall why we were interested in finding these binary numbers that behaved in a certain way through the odd step of the Collatz conjecture. And my idea was that, we had this reshuffling going on under the Collatz conjecture in the odd step, that when we multiply by 3 and add 1, the binary pattern of ones and zeros changes, and the n over 2 step only knocks off these these zeros. So my question was, is there a series of numbers that behaves so that after 2 steps through the Collatz conjecture they turn into powers of 2? And so the simplest example of a number in that case is 3, right? So 3 goes to 10, right, after the 3n plus 1 step. Then we divide by 2, and we've got 5, right, which at this point we should recognize is a precursor to a power of 2, in this case 16. There are lots of other numbers. 13 is another example. 53, 113, 213. I'm not going to prove how I found these in the video. I have a computer program that I wrote in Python. I'll put the link in the description of this thing. It'll link to the GitHub program if you want to run it. It's a little bit, it's a little bit rough, but it should be pretty easy to figure out. So yeah, we've got this sequence of numbers that goes on, right? And so I think naturally you find this sequence and you're like, oh, well, maybe like before where we had that lovely pattern in ones and zeros, maybe there's a really nice pattern here that's simple. And unfortunately, that's not the case. You don't have a nice pattern here. So 3, the simplest example, is 1, 1. But then with 13, we have 1, 1, 0, 1 in binary. And then we have, for 53. And so you see these two and you're like, oh, I noticed some stuff in here, right? Like I noticed this 1, 0, 1, 0, 1 pattern and this 1, 0, 1, 0, 1 pattern here. So you think, oh, maybe I've got a sequence, right? But then you get to 113 and all of a sudden you've got 1, 1, 1, 0, 0, 0, 1. So, if there is a pattern that pops out, it's not immediately apparent in the same way. And in fact, if you recall our previous pattern, our pattern of 1, 0, 1, 0, 1 going on, this sequence here actually exists in the online encyclopedia of integer sequences. Just pull up that sequence here, and it's sequence A00 2450. And so it was well known when I'd found it. It's not like I had a unique discovery, but it was still neat to find it on my own. Got a bit of a thrill. And one thing about the sequence is it has an ordinary generating function. That is a really nice compact representation. So that the way they write it on the OEIS is a to the n, is equal to 4 to the power n minus 1 over 3. So this is our first sequence we found. And then over here we've got our second sequence of numbers. And unfortunately, at least based on taking the sequence that was generated in my program and plugging it into the OEIS, I didn't find another nice sequence. But there are these classes of numbers that turn into powers of 2 after 2 rotations, 2 steps through the 3n plus 1 step of the Collatz conjecture. So even though my initial idea was correct, in that there are these classes of numbers. It doesn't break down into a nice, easy pattern like the first one. So things were a bit more complicated than I thought. But yeah, I had some other ideas that were sort of sparked from that. So I'll talk about those in the next video.